Welcome to Dare to Know, interviews with quality and reliability thought leaders. I'm Tim Rodgers, and today I'm pleased to welcome Mike Konrad. Mike Konrad is an industry expert on the removal of contamination from circuit assemblies. He's been part of the electronic assembly cleaning industry for the past 33 years. Mike designed several automated cleaning and cleanliness testing machines. He's published scores of technical articles on the subject of cleaning and cleanliness assessment, and he's been a member of editorial boards for several industry publications. Mike served on the U.S. Navy's EMPF Manufacturers Committee, and he's a featured speaker at industry events and technical workshops worldwide. Mike was honored with Distinguished Speaker status from the Surface Mount Technology Association in 2017. Mike has also served as a court-appointed expert witness in civil litigation matters concerning post-reflow cleanliness assessment and contamination-related failure mechanisms. He's the founder of Aqueous Technologies, a manufacturer of automated cleaning and cleanliness testing systems designed for the electronic assembly industry, and he served as the CEO and CTO of Aqueous Technologies since 1992. Mike is also the host of the Reliability Matters podcast, which you can find on iTunes, Spotify, Spreaker.com, and Reliability.fm. Mike Konrad, welcome and thanks for joining us.
Hey, who is that guy? I want to hire him. Thank you. Thank you, Tim. Well, it's always awkward. It's always awkward to hear your own bio because it's just
I have a tough time. I have a tough time with that myself. So luckily I don't have to repeat that.
Yeah, when I do a lot of speaking workshops and they always want to read my bio and I go, no, don't let that takes away my time. It takes away my time.
That can't be me. That can't be me they're talking about.
Well, thanks for inviting me on your show. I really appreciate it, Tim.
Mike, Aqueous Technologies specializes in cleaning and defluxing equipment for the printed circuit industries. I'm sure some of our listeners might be surprised to hear that printed circuit assemblies still need to be cleaned. Can you give us a little history and explain why this has become a bigger issue?
Sure. It's funny because you get two sides of the equation, those that are people who are surprised they're not cleaned and people who are surprised they are cleaned. And it just depends on which side of the fence you're on, I suppose. So just to put things in perspective, a little historical content, there was a dividing line in our industry in terms of a date, and that date was 1989. Everything before 1989, the boards were cleaned before 1989, almost universally, very, very few exceptions. And when I mean cleaned, the purpose of cleaning is primarily to remove the flux residues after soldering or after reflow. Flux is either a water base or a pine sap base, rosin base, could be a resin based, but best practice was always to remove the flux after reflow, after soldering. But in 1989, the U.S. government and 10 other countries, 11 countries altogether, signed a treaty in Montreal, which is now referred to as the Montreal Protocol. And what the Montreal Protocol did was to publish data indicating that certain chlorofluorocarbons, chemicals, CFC-based chemicals, these chlorine molecules were escaping the atmosphere and going up and chewing on ozone like a Pac-Man game. And today's environmental mantra is global warming or climate change. Back then, in the late 80s, early 90s, it was ozone depletion. And if the ozone were to be depleted due to mankind or just nature, that would pose a grave danger because the ozone, of course, absorbs a lot of the UV rays, which otherwise would instantly give us skin cancer and give us severe sunburn. So scientists realized that man was contributing to that problem and they wanted to counteract that. So there was a ban placed on the production of certain CFC-based chemicals. The two most common chemicals in the electronic assembly cleaning industry were 1,1,1-trichloroethane and a special blend of Freon sold by DuPont called Freon TMS. And the government and 10 other countries said basically in 1989, we'll give you all 10 years to figure out what to do. Come up with another solvent or come up with another cleaning method, or whatever you want to do. But after 1999, you're not going to be able to make this stuff anymore. And no one really took it seriously the first several years because they figured that's so radical. It would be like the government banning gasoline in 10 years. Unless you come up with some other plan, it's not going to happen. But it did happen. And necessity being the mother of invention, two things happened. Number one, there were alternative cleaning agents developed that frankly weren't that good, but at least they weren't eating up the ozone. And the greater accomplishment was a new flux formulation was developed in the very late 80s, very early 90s, which has been referred to as no clean flux. In other words, solder all you want, reflow to your heart's content. The residue that it leaves behind is almost nothing. Don't worry about it. It's benign.
Right.
It's inert. You'll be fine. So, of course, given the choice, those who didn't have to clean because they were cleaning to a standard, what we like to call class 1, class 2 manufacturers, office equipment, and Game Boys and cell phones and non-critical things, they just stopped cleaning. That's 80% of the electronic assembly industry. They just stopped cleaning overnight. And the people who had to clean, the space people and the aerospace people and medical people, they kept cleaning. They just found other ways. But about 80% of the market converted to just not cleaning at all. And so cleaning virtually went away. Hence the question, I'm surprised we're still cleaning.
Yeah. So, Mike, I'm sorry. The reason cleaning went away was primarily a cost issue. People just were trying to avoid the cost.
Sure, because otherwise they would have to invest in different cleaning solvents or cleaning medias, and those cleaning medias required different types of equipment than what was being used before. And if you can get away with a process, even if you don't have to buy new equipment, if you can just stop doing something and have your boards completed sooner, it's a cost savings. It's a space savings, it's a cost savings, energy savings, et cetera.
Good point.
One less thing to go wrong. So there was a lot of reasons for people to jump the cleaning ship and just follow the label, which says, no clean, almost like no clean. And about 80% of the industry, as I mentioned, stopped cleaning within a very short period of time. And that was wildly successful for a very long time. It's different today, and I'm happy to get into the reasons it's different today. But, we got away with a couple of decades of not having to clean, except the people who are required to clean because they have a standard that they're meeting.
Do you think that kind of lulled people into a false sense of security or something? I'm not sure how to ask this, but do you think people got sloppy and maybe were a little less careful about how they applied their flux because they didn't have to worry about cleaning?
In many cases, yes. And I think more importantly, the industry reacted rapidly when they heard no clean flux was a thing.
Yeah.
And then when they heard more recently that no clean flux isn't what they thought it was anymore, for reasons I'll be happy to explain, they're much slower at bringing back a cleaning process than they were at getting rid of one. So there was almost an overreaction, maybe too quick, to adopt a no cleaning culture within their manufacturing floor, and equally harmful, a delay, an underreaction in addressing the issues that not cleaning is now witnessing, and being a little too slow to remedy it. So too fast to initiate it, too slow to correct it.
Yeah. Well, again, not surprising given the cost implications. So why has this become, I'm sorry, you may have explained this, but what's the urgency now? What are some of are there design changes or other things that are causing this to become more of an urgent issue?
Right. Well, I'll give you a little quiz, and I'm absolutely 100% sure you're going to get it right. Circuit boards are getting larger, or they're getting smaller?
Right.
Smaller, right? So smaller, clearly. And when we call that miniaturization in our industry, which can apply to a lot of different industries, but in our world, we talk a lot about miniaturization. Circuit boards and components are highly, highly, highly miniaturized. And there are components, and probably the podcast is I can't hold it up to the microphone and show you, but there are components that you could fit maybe 50 of them on the edge of a matchstick, right? A matchstick that
Right.
you get in a bar, not a big
Yeah.
flame, not a big, torch lighting matchstick or cigar matchstick, but a normal paper matchstick. You can fit probably 50 of them on the tip of a matchstick. They're so
Yeah.
small. And that has allowed wonderful things in our industry. It has allowed us to produce, supercomputers that can also make phone calls that we can put in our back pocket. It allows us to have very small circuit boards doing very large functions. And the result of that is quite literally thousands of components soldered to a very small postage stamp sized circuit board.
Sure.
And before miniaturization, boards were rather large. Components were known as through-hole components back in the 80s, which means they had a lead that went through the board and got soldered on the backside of the board. And there was a huge geography, this huge space between the conductors, between the cathodes and the anodes, between the polarities of the components. Today, we've replaced that space, kind of like an urban downtown center. We find one small little plot of land and we build up and put a bunch of high density housing on it. The same things happen with circuit boards.
Right.
So the amount of space between conductors is extremely small. In fact, in some cases, you can't see it with your eye. You have to see it under magnification.
And let me guess, flux residues have not gone through the same miniaturization?
No, the molecules are the same size. The ingredients of that material are about the same. There's been all sorts of improvements in terms of solderability and other helpful things, but in terms of the amount of conductive corrosive material within a given volume of flux has stayed the same. So what's happened are circuit assemblies are now tolerating residue far less. So the residue tolerance of a circuit assembly that's been miniaturized, which is pretty much every circuit assembly, is much, much lower than it was when it was a larger circuit assembly. The other thing too, though, that I teach a lot of workshops around the world, and I always love getting those aha looks back, like, oh my God, I never thought about this. The other big thing is when we stopped removing flux, because we came up with a technology that didn't require removing, we stopped removing everything else. And when boards were cleaned, when they ran through a defluxing process, a really more accurate way to describe that process is not really a defluxing process, it's a cleaning process, because
Sure.
we were removing flux, which was the contaminant we intentionally added to the board. But there are a host of contaminant species that I like to call the usual suspects that stow away onto the board from board fabrication, from component fabrication, from various parts of the assembly process, from humans. We're dirty little creatures and we tend to touch boards after we've touched other things. And all of that, I call it the Dorito effect, all of that transfers to the board, which no one really considered back in the day when we were cleaning boards, because
Right.
we targeted the flux and everything else came off with it. Now that we're not targeting flux, we're not targeting anything. So the totality of residues and the tiny, tiny gap that they're filling is enough to trigger all sorts of failure mechanisms, mainly electrochemical migration, which manifests itself in several ways.
I assume that leads to shorts, but I'm guessing you could have opens as well.
Yeah, really, it leads to shorts. You're right on there. So imagine, all the electrical engineers that are listening to this. Just imagine a circuit board that's plugged in, and then just take metal shavings and just sprinkle them on the board, like right, and just watch the fireworks begin. That is exactly the effect that's happening when electrochemical migration gets hold. So what happens is one of a few things. Electrochemical migration basically is a process of covering insulating materials with conductive materials. So it's like running aluminum foil across the board, right? It'll just short from A to B. And electrochemical migration requires, it's basically metal plating. When one chrome plates a bumper, as we did when we were kids, we chrome plated everything in the car. Now it's all plastic. You can't really chrome plate it, but it's a metal plating shop. You have a source metal, you have a target metal, you have conductive solution, and you have an electrical charge. And metal basically dissolves off one side and redeposits on the other side. The same exact phenomenon happens on circuit boards when certain conditions are present. And those conditions, there's three main ingredients required for electrochemical migration or for chrome plating for that matter. One is you need current, electrical current. You need a bias, which of course every circuit board has. Number two, you need a conductive corrosive material. That could be flux residue. That could be the totality of all the usual suspects that have stowed away on the board. And number three, you need moisture. Now, I don't mean like puddles of water, moisture. Right. So you're in Colorado, right? Am I right in saying that?
That's right.
Okay. Well, you don't get a lot of humidity, but imagine being in Mississippi or anywhere in the southeast, in
Sure.
Miami in August. That is a huge moisture-rich environment. So a circuit board that has been miniaturized, that has not been cleaned, that has some conductive corrosive surface, that is plugged in and is running, that is in Miami in August. It has all three ingredients required to contribute to an electrochemical migration event. And electrochemical migration, as we call ECM, because we don't like to say big words, ECM can manifest itself in basically three ways. One, the most dramatic and the most common is dendritic growth. That's what you were referring to, Tim, when you said, the metal across the board.
Right.
It actually grows a metal crystal. So it's copper or tin or whatever metals are on the board already will start growing a metal crystal, and it looks like a tree. In fact, the word dendrite comes from the Greek word dendron, which means tree, or dendrites, which means tree-like. It looks like a tree. It's a tree branch growing from a cathode to an anode, or from an anode to a cathode, depending where on the board it is. And when it reaches the other side is when the fireworks begin. When it reaches the other side, it's a short. And that short can result in either the dendrite just popping like a fuse and no further drama, or more frequently, it generates a lot of heat. The board catches fire. And because we tend in our business to put boards inside things to make them run, the things catch fire. And
Sure.
that is a real problem. The other manifestation of ECM is something that's just frustrating beyond belief. It's called parasitic leakage. And parasitic leakage is not enough electrical leakage to generate a direct short. It is, though, enough electrical leakage to reduce the amount of conductivity on the board. So it might do things like drain a battery. If a board is run by a battery, it'll drain the battery unexpectedly. Sure. Or it might just cause a sensitive instrument not to calibrate or not to function quite properly. So
could it cause a bit not to flip or something?
It could cause a bit not to flip. What it normally does, though, is it just reduces the dielectric properties of the board. It reduces the resistive properties of the board and allows a little unexpected current to go back and forth, which, depending upon the nature of the transistor, it might take that as an instruction. It could just drain a battery. It could just cause part of the board to get warm. It could cause a sensitive instrument not to calibrate. It could do all sorts of nasty things. But what makes this problem particularly frustrating is it's temporary, which sounds like a good thing, but that's what makes it frustrating. So let's say someone in a hot and humid environment is using this instrument and it won't calibrate. So they send it back to the manufacturer, and the manufacturer's in Denver, and they're in a climate, it's pretty low humidity there anyway, and they're in a climate-controlled, humidity-controlled environment. They test the board, and they get, for any test engineers on this podcast, you'll be familiar with two terms. The first term is NTF, no trouble found.
Oh, yeah.
You can't duplicate the problem. And usually after a couple of times back and forth, NTF is replaced with another acronym, which is WTF, which I'll let your listeners figure out what that is. So NTF, WTF, send it back to the customer. The customer must be doing something wrong. The customer plugs it back in, getting assurances everything's perfect. And of course, it's still humid, so it malfunctions, and they point fingers at each other. That's the frustrating part of parasitic leakage. Then there's some other manifestations of ECM, which are less common, but they all have their genesis in cleanliness, in conductive corrosive residue. That's one of the three ingredients that are required for ECM to take effect.
Mike, I don't know. I don't want you to give away any of your client names, but I wonder if you've worked with any companies that were having these kinds of problems. And then after they implemented better cleaning techniques, started seeing some improvement.
Yeah, I'll tell you my favorite story because it's very low tech, and I think a lot of people can identify with this. So we had a customer who manufactured stage equipment, amplifiers and speakers and things like that. And these guys were legit. They sold to major bands, and it's not the stuff you bought at Guitar Center. It's major stuff. And over the years that they were in production, they went from tubes to solid state, from through-hole technology to surface mount technology. Those are just a description of the type of components. And I would imagine, old audiophiles will swear by tubes, and swear by record players. You got to have a tube, you got to have a piece of vinyl. That's the best sound on the planet. Well, that may or may not be true. But what happened in their case is along the line, they switched to a no clean flux like everybody did. And clearly, if their stuff if it fails, nobody actually dies,
Right.
Might be embarrassing, but it's not a life or death situation. So they found, though, that they were having trouble with the quality of their sound. There was some kind of distortion or feedback or some less pure sound coming out of some of their amplifiers. And one of their engineers, connected the dots and said, things used to sound good when we clean. They don't sound good now that we don't clean. So we think maybe it's residue. So they sent boards to us because we build cleaners and we build testers. Machines that clean boards, machines that test boards to see how well the machines that cleaned boards worked.
Right.
And long story short, we offered to clean boards, and then we offered to subject them to a battery of analytical tests to show them how clean their boards are analytically. And they went, nah, we don't understand that stuff. We're just a bunch of musicians. We don't care about whatever numbers you perform. We have our own way of testing boards for cleanliness. What do you think that was? They plugged them in and they jammed, right? And so they determined what I love to call, when all the workshops and webinars and all the stuff I do, I always end with this story. They coined the term that I like to call the sound of clean. They determine what clean sounds like. Now, other people can't do that. Everyone has to have their own quote unquote sound of clean. And usually it's an analytical test. They get a number or whatever. But this was a case where their boards, their end product would not function properly because they stopped cleaning and they left residues. And they cleaned it, and now their boards and their product functions properly. Now we can take that same application and that example, and we can apply it to aerospace. We have NASA as our customer, Boeing's our customer, Airbus is our customer, Rockwell Collins, Northrop Grumman, Raytheon. These are all people that build things that if the products fail, people die. Yeah. So they clean. They don't clean as a matter of elective. They clean as a matter of requirement. And they have strict standards that they have to clean to and test to. And so we have those people who clean, and then we have those people who go, what's cleaning? We haven't heard of cleaning. So that's why we do so much education. That's why we do podcasts and webinars and workshops, because people either already know about cleaning or more commonly have no clue about cleaning or remember it from the past.
Right. So, Mike, do you have any advice for reliability engineers and managers who are trying to trade off the cost of failure versus the cost of implementing or re-implementing a cleaning process?
Yeah, that's a great question. I like to talk in some of our educational efforts about the barriers to cleaning. What are the obstacles to cleaning? And I ask people, what's the reason you're not cleaning tomorrow? If you know cleaning will solve a problem, why are you fighting it? It's like, sorry to be crude, but it's like lying in bed at night. You got to go to the bathroom, but you just don't. And then finally you do, and they go, "Why? Oh, I stayed up for an hour putting that off. Why didn't I just go? It takes 10 seconds." It was never that difficult, right? So, and cleaning is kind of, I don't want to equate cleaning with that, but it's similar in an example. I ask people, what's the obstacle? What's stopping you from solving this problem now and moving on to something else? And they go, well, it's the cost, it's the space, it's the environment, it's whatever. And then we show detailed analysis that shows by the time they buy the equipment and amortize it over 5 or 7 years and pay for the the chemicals in the water and whatever. It costs about 3 cents. 3 cents,
Wow.
$0.03, 3
Wow.
cents per assembly to clean. And that's in zero discharge environment. So nothing touches the drain. And then, so we tell people that, and they have this kind of, oh, shoot, look, like we've been putting this off for so long. Is that really how much it costs? And they're skeptical, of course, but the numbers prove themselves out time and time and time again. And then does it slow down the process? Sure it does, because it adds an extra 30, 35-minute cycle to a group of assemblies.
Right.
So it does slow down the process, but then, how much does issuing an RMA cost, and how much does testing the board, and how much does, being sued costs, or worse? In fact, in the bio you read, you mentioned that I've been hired as an expert witness, and that's true. I was an expert witness for a company that they were a contract manufacturer. They assembled boards for a living, and their customer told them, here's our board, here's our statement of work, build it just like this. And they did. They should have known better, because it wasn't a proper statement of work. It didn't follow best practices. And they skipped a cleaning process, and 60,000 boards failed, and nobody died, but it cost a lot of money, because these boards were buried in the ground in various sites throughout North America.
Wow.
And somehow in depositions, when people ask me, well, how much does it cost to clean? And I tell them it's 3 cents. You could see them losing the case right then. Like, really? You put all this at jeopardy? You put millions of dollars in repair expense, and potentially people's lives, because it was a kind of a high rail device, potentially people's lives at risk because you wanted to save 3 cents. A jury's not going to like that, so they settle right away.
It really puts it in perspective.
It does, exactly. It's not an expensive process, and it will not make your life better in many ways. Your dog will still bark at strangers, and your car won't start once in a while, and all that kind of stuff. But one thing it will take away is all possibility of electrochemical migration. There could be a million other things in your life that'll go bad, but that won't happen if you clean boards. You will never experience an ECM failure if boards are simply clean.
Makes sense to me. Mike, this has been great. Thanks so much for being with us.
Well, my pleasure. Thanks for inviting me, Tim. It's been a joy.
That was Mike Konrad, CEO and CTO of Aqueous Technologies and host of the Reliability Matters podcast. You should definitely check that out. This is Tim Rodgers. Thanks a lot for joining us.